Hi, I'm Raunak, and Harkeerat, Prabhleen, Namratha, and I have prepared a few lessons on Unit 7, the financial applications of what we've learned in previous units. For the lessons, I will be starting with simple interest and compound interest, followed by Harkeerat, who will be talking about present value. Next, Prabhleen will be talking about annuities, and finally, Namratha will be talking about present value of annuities. Here are the learning goals for this unit. You can pause the video now if you'd like to read them. Before we get started, let's go over a couple of definitions. Principal is the amount of money in dollars that was initially invested or borrowed. The annual interest rate is the rate at which interest is charged on the principal amount, as a percent per year. This is expressed as a decimal when doing calculations. Amount is the value of an investment at the end of a time period. Amount is calculated by adding the principal and the interest earned by the end of the given period of time. Compounding period is a period of time after which a compound interest is calculated. Present value is the principal invested or borrowed today that results in the given future amount according to given interest and time. Future value is the amount that a principal invested or borrowed will grow to according to given interest and time. Let's start with our first lesson, simple interest. Simple interest is interest that is applied to a principal amount for the entire duration of a loan or investment. This means that if you invest using simple interest, then the interest that you earn each year is based solely on the principal amount you initially invested. The formula for simple interest is IE equals PIT, where IE equals interest earned, P equals principal, I equals annual interest rate expressed as a decimal, and T equals elapsed time in years. Since the amount is defined as the principal plus the interest earned, we can say that A equals P plus PIT, which can then be simplified by factoring out P to P bracket 1 plus IT close bracket. Therefore, amount is calculated using the formula A equals P open bracket 1 plus IT close bracket, where A equals amount, P equals principal, I equals the annual interest rate expressed as a decimal, and T equals the elapsed time in years. Let's do a sample problem. G Hall invests $3,000 at 7% simple interest per year. Develop a linear model to relate the amount to time. Identify the fixed part and the variable part. So here's my solution. P equals 3,000, I equals 7% or 0.07, and T is unknown. I've taken my known values and plugged it into the formula for amount. I've then fully simplified to get 3,000 plus 210T. The fixed part here is 3,000 and the variable part here is 210T. How long will it take for the investment to triple? So here we have our linear model, and now we want our amount to be tripled and solve for T. So here I've multiplied our principal amount by 3 to get 9,000, and then I've isolated for T over here and solved for T, 6,000 divided by 210, to get 28.57. Therefore, it will take approximately 28.57 years for the investment to triple. Lesson 2 is about compound interest. Compound interest is interest that is calculated at regular compounding periods. Contrary to simple interest, compound interest is calculated based on the amount that is left after each compounding period. Compound interest is widely used in the real world. The graph below shows the relationship between simple interest and compound interest. Deriving the formula for compound interest is simple. By the end of the first compounding period, we get P plus PI. This P plus PI is then used as the principal amount for our second compounding period. When simplified, we get A at the end of the second compounding period is P bracket 1 plus I close bracket squared. This pattern continues and we get a formula for compound interest, which is A equals P bracket 1 plus I close bracket to the power of n, where A is the amount, P is the principal, I is the annual interest rate per compounding period, and n is the number of compounding periods. Before we do any calculations, we must set up our I and n values. The number of compounding periods, or n value, is found by multiplying a given time in years by the compounding period factor. The interest rate per compounding period, or I, is found by dividing the annual interest rate by the compounding period factor. Below are the compounding period factors. Annually is 1, semi-annually is 2, quarterly is 4, monthly is 12, bi-weekly is 26, weekly is 52, and daily is 365. Let's finish lesson 2 with a sample problem. Arman invests $5,000 at 6% compound interest for 3 years. How much will Arman have after 3 years if his interest is compounded A, monthly, and B, semi-annually? Let's start with A, where his interest is compounded monthly. Our I value in this case would be 0.06 divided by 12, since 12 is our compounding period factor. Our N value, or number of compounding periods, will be 3 years times 12, which is 36 compounding periods. When we sub in our values into our formula, A equals P bracket 1 plus I close bracket to the power of N, we get 5,983.40. Therefore, if Arman's interest is compounded monthly, he will have $5,983.40 after 3 years. Moving on to part B, where his interest is compounded semi-annually, our principal amount is the same. Our I value is now 0.06 divided by 2, since our semi-annually compounding period factor is 2, and our number of compounding periods is 3 times 2, which gives us 6 compounding periods. When we sub in our given values into our formula, we get 5,970.26. Therefore, if Arman's interest is compounded semi-annually, he will have $5,970.26 after 3 years. What is the amount of interest earned if Arman's interest is compounded monthly? To find the amount of interest earned, we do IE, which is interest earned, equals amount minus principal. When we sub in our amount for our compounded monthly answer, and we sub in our principal amount, which is $5,000, 5,983.4 minus 5,000 gives us 983.4. Therefore, if Arman's interest is compounded monthly, he will earn $983.40 in interest.
Unit 7 is the present value of compound interest. In this unit, you will be expected to understand the definitions of future and present value, and to be able to rearrange the compound interest formula to solve for present value given a future value, interest, and time period. In Unit 7.2, you learned about the amount and principal. Future value is another name given to the amount, and present value is another name given to the principal. This is the formula you were given in the previous unit. We can replace amount with the future value represented by FV and principal with the present value represented by PV. This unit will ask you questions to find the present value given a future value. In order to do that, we can isolate PV by dividing both sides by 1 plus I to the power of n. We're given a fraction. To simplify it, we can separate it into FV times 1 over 1 plus I to the power of n, and then flip the fraction by raising it to the power of minus 1. This gives us our final formula for present value. Let's solve an example question. Ishmeet wants to invest money now to have $1,000 in 6 years. If she invests her money at 5.75% per year compounded quarterly, how much does she need to invest? First, let's list all of our givens. The future value is $1,000, and interest is 5.75% divided by 4 because it's compounded quarterly. The number of compounding periods is 6 years times 4, giving us 24. Let's plug in all of these values into our formula. This gives us $709.96. That's how much money she needs to invest now to get $1,000 in 6 years. Another question asks, Amandeep wants to borrow some money now to buy a motorcycle. He estimates that in 5 years he can pay back an amount of $12,000. Bank 1 charges 8.9% interest, compounded semi-annually, and Bank 2 charges 8.4% interest, compounded monthly. Which of the two loans is the better option and why? Let's list all of our knowns first. The future value is $12,000 either way, but for Bank 1, the interest is 89% divided by 2 because it's compounded semi-annually. The number of compounding periods is 5 years times 2, giving us 10. Now we can list our information for Bank 2. Let's sub in our Bank 1 information to find how much we can loan. The present value is $7,764.20. Now for Bank 2. This gives us $7,896.11. As you can see, Bank 2 gives us the better option because we're able to loan more money while still paying only $12,000 after 5 years.
An annuity is a series of payments of equal value made at regular intervals. A timeline illustrates an annuity. To draw a timeline, you divide a line into the number of compounding periods and write the regular payments underneath each compounding period. The last payment incurs no interest since it was made at the end of the compounding period and there are no more compounding periods after it. To calculate the end value of each regular payment, you multiply it by 1 plus I to the power of compounding periods that have passed since the payment was made. For example, the second last payment will have an end value of regular payment times 1 plus I to the power of 1 since one compounding period has passed. The third last payment will have an end value of regular payment times 1 plus I to the power of 2 since two compounding periods have passed, and so on. This is a geometric series with the common ratio of 1 plus I. Hence, we can use the formula for the sum of geometric series to come up with the formula for an annuity, in which the future value of an annuity is equal to the regular payment times 1 plus interest rate for the compounding period to the power of compounding periods minus 1 over the interest rate. We can rearrange the same formula to calculate regular payments when the future value, interest rate, and the compounding periods are given. Now we'll apply our knowledge of annuities to solve a sample problem. Avni needs to have $34,965 in 14 years for the down payment on a house. To do this, she makes monthly deposits in an annuity. She has two options for investing. Plan A, 4.8% per year compounded daily, and Plan B, 4.6% per year compounded weekly. Determine which plan is better for Avni and explain. From the question, we can extrapolate that the future value of the annuity must be $34,965 at the end of a period of 14 years. Since Plan A gives an annual interest rate, we must divide it by 365 since it is compounded daily. N in our case denotes the number of deposits that Avni makes, which is 14 times 12. Since Avni is making monthly deposits, which is an amount of 168. We use the formula with regular payments since all the variables in the right hand side are given. And then we simply substitute all of our variables in and we come up with this equation. Once you punch this in your calculator, you come up with a value of $205.85. This is the amount that Avni must pay monthly to have an end value of $34,965 after a period of 14 years with Plan A. With Plan B, since the interest rate is again given annually but compounded weekly, we must divide it by 52. And our number of deposits over our time period remain the same since Avni is still making monthly deposits, which is 168. We once again use the same formula for regular payments since all the variables on the right hand side are given. And once we substitute all of our variables, we come up with this equation. Once you punch this in your calculator, you come up with an amount of $193.13. This is the amount that Avni must pay monthly with Plan B to have an end value of $34,965 at the end of the period of 14 years. Since the monthly payments of Plan B are cheaper than that of Plan A, and yet Avni still has the same end value of $34,965 after a period of 14 years, Plan B is the better option.
Moving on, 7.5 is a lesson that will focus on the present value of annuities. The present value of an annuity is used to determine the total amount that finances a series of regular withdrawals over a specific period of time. The formula for present value is as stated over here, where PV equals R times 1 minus 1 plus I to the power of negative n divided by I. To derive this formula, we can use a simple timeline where there are a series of R amount of withdrawals. Using our knowledge from 7.2, we find out that the present value needed for this R amount is this. At compounding period number 2 is equal to this, and compounding period number n equals this. Now we want to find the present value that will account for all of these withdrawals. So we need to add this plus this plus this. When we do so, we find out that this is a geometric series. So using our knowledge from Unit 6, we find the common ratio and the initial value. Now since we are dealing with the sum, we can use the formula that will give us a sum of a geometric series and simply replace the values because we have the a value and the r value over here. And after replacing and simplifying the formula, we find out the formula for present value is equal to this. In this scenario, PV equals present value, R equals the regular withdrawal, N equals the number of compounding periods, and I equals the interest rate per compounding period. So if you use the diagram below, the future value always depletes to 0 because we begin with the present value, let's say X amount, but because there is a series of regular withdrawals, you end up with a future value that is always equal to 0. Now let's take a look at some examples. In this scenario, we have Josh, who is putting his summer earnings into an annuity where he can withdraw living experiences when he's at university. So he needs to withdraw $900 per month for 8 months, and interest is earned at a rate of 6% compounded monthly. So we can draw a timeline to represent this annuity, as stated over here. And we know some information. So we know the R is $900. We know the N equals 8 compounding periods because it says 8 months in the question and it's compounded monthly. I equals 6% annually, so 0.06. But this is compounded monthly. So since there are 12 months in a year, we divide 0.06 divided by 12, which is equal to 0.005 per compounding period. So we're trying to find out how much Josh needs to invest at the beginning of the school year, so the present value. So as we just learned the formula of present value, we can simply sub in the known values into the equation because we know R, we know I, and we know N. After doing so, we can evaluate the equation and we find out that the present value is $7,040.66. Therefore, Josh needs to invest $7,040.66 at the beginning of the school year to finance this annuity. We have example number 2. So Fiona's total life savings are $300,000 and she wants to plan an annuity where she can have constant withdrawals quarterly for the next 30 years, and the annual interest rate is 5.2%, which is compounded quarterly. So how much can she withdraw each quarter? So we know the known values PV, N, and I. N is 120 because it's 30 years, however it's compounded quarterly, which is equal to 120. And I is 5.2% annually, but because it's compounded quarterly, we divide it by 4, which is equal to 0.013 per period. We rearrange the present value formula to find for R. Once we do so, we substitute the values and simply solve for R. Where we end up with the result 4950.87. Therefore, Fiona can withdraw $4950.87 for every quarter for 30 years. Thank you for watching our video.